In this section, we'll take a look at rotation of axes, in particular how they pertain to conics.
Consider the following ellipse. Notice that it does look like a typical ellipse. It has a major axis, it has a minor axis, and it would have a couple of foci around here along the major axis, and it would have a center right there at the origin. But unlike any of the ellipses that we've seen so far, in fact, unlike any of the conic sections we've seen so far, none of our axes line up with the x-axis or the y-axis. Up until now, every ellipse we've had has had a major axis that lines up either with the x-axis or the y-axis. Same thing with a parabola. The latus rectum and the directrix line up either with the x-axis or the y-axis. And same thing with a hyperbola. The transverse axis would line up either with the x-axis or the y-axis. Up until now, every conic section we've seen has had some axis that lines up with either the x or the y-axis. So what happens when you have a conic that doesn't? Well, this is still an ellipse, so it should still be expressible using the same notation, using the same kind of formulas that we've had for a conic. But how do we account for the fact that there's a rotation? Or do we even have to? So as it's going to turn out here, what essentially we're going to want to do is this. We're going to want to say, well, these axes are not lined up the way we want them to. Okay, so what do we want to do? Let's rotate it. If you rotate it just the right amount, this is now perfectly horizontal and this is now perfectly vertical. Okay, now that's a little easier said than done. Right? Obviously, taking a sheet of paper and rotating it, moving it around a bit, is probably a little easier than the mathematics that it takes to actually perform that rotation. However, that is essentially what we're going to want to do. We're going to want to say, okay, this is our current situation. We have a coordinate axis, the x and y plane. In fact, let's go ahead and label that. Here's our x-axis and here's our y-axis. But what we would like to have is a coordinate axis more like this. We'd rather have these be the x-axis or the y-axis. That way, this is perfectly lined up with the x-axis, and the minor axis is perfectly lined up with the y-axis, the way I'm used to. Now, just because I wish this was the x-axis doesn't mean it is. After all, this is the x-axis. Oh, but we're going to treat this as if it were the x-axis. So what we're going to do is we're going to label it in a way that distinguishes it from this one, but still shows that it's related to this one. We're going to call this x prime. And this one is going to be our new y-axis. So we're going to call this y prime. And essentially what we want to do is we want to find a way to mathematically model what it takes to take a rotation of an axis, to take this xy plane and rotate it until we get this as our x and y plane. Here's going to be an angle from the x-axis to the x prime axis. We're going to call that angle theta, as usual. Okay, so we're going to need to do two things. One, we're going to have to figure out, okay, what is that angle theta? And two, we're going to have to figure out, if we know what that angle theta is, can we figure out how to rewrite our equations in such a way that we line up with this new coordinate axis, which is offset by an angle of theta. All right, so that is ultimately what we need to have happen. Okay, so how do we do that? Well, consider some point that's on your conic. Here's a point. And okay, there's a different expression if I'm expressing in terms of x and y, or if I'm expressing in terms of x prime and y prime. But no matter how I express it, it is the same point. It's that point right there. Okay, so let me label that point xy, and let me consider that point in polar coordinates. And so let's consider what it takes to get from here to here. All right. Well, in polar coordinates, you have a distance and you have an angle. All right. Well, the distance from the origin to that point will always be the same, regardless if I'm dealing with the original coordinate axis or the new one. We'll call it r, whatever that might be. So now our angle, well, if you're dealing with the x prime, y prime plane, then the angle that it takes to get you from the x prime axis up to this direction is this little angle right here. We'll call it, well, we already have a theta here, so we'll call this one alpha. Another common name for an angle. All right, now the angle to get from the original x-axis up to this line would be the sum of those. So here, this little one takes you from x prime to your point, that's alpha. And then to get from the original x to your point, you're going to want to go theta plus alpha. All right, so we're going to take advantage of that. All right, keeping with just the x prime, y prime plane, we know that in polar coordinates, x is equal to r cosine of the angle. Right here, we're dealing with not x, but x prime, so I'm going to use that notation. X prime is equal to r cosine of, and then we have that angle. We're not using theta, we're using alpha, because right now we're using the x prime, y prime plane. So that's x prime is equal to r cosine alpha, and we have y prime is equal to r sine of alpha. And that's the typical way of expressing x, y coordinates in the polar coordinate system, r theta, or in this case, r alpha. And then we can do the same thing for this point relative to the xy plane, the original xy plane, by saying, okay, x is equal to r, that distance, times the cosine of the angle that it takes to get you from x up to that point. Okay, well, that's theta plus alpha. Okay, so theta plus alpha. And then y is equal to r times the sine of that angle, which again, theta plus alpha. But so here's the thing. Since these are expressed as the sum of angles within a sine or a cosine, we know how to handle that. We have sum and difference formulas for sine and cosine. So using this first one, we can say, so x is equal to r cosine of theta plus alpha. I've just rewritten that first line. But by the sum formula for cosine, that's r times, and we're going to replace cosine of theta plus alpha with the sum formula for cosine, which will be the cosine of the first angle times the cosine of the second angle, cosine theta cosine alpha, minus the sine of the angle theta times the sine of the angle alpha. Like this. Well, notice if we distribute our r, we get r cosine theta cosine alpha minus r sine theta sine alpha. But notice that r cosine alpha, that's your x prime. So here, r cosine theta, that's your x prime. And over here, r sine of alpha, that's your y prime. So you can write this as, well, that's your x prime times cosine theta. And you can write this minus, that's your y prime times the sine of theta. This substitution, we can take x and write it as x prime cosine theta minus y sine of theta, is what will allow us to convert things from the xy plane into this much simpler x prime y prime plane. Not simpler in terms of the expression, because of course we're going to have to perform the substitution, but simpler in terms of the conic. Everything will line up to this new coordinate axis. Likewise, we can do the same thing for y. So here we have y is equal to r sine of theta plus alpha, like this. But of course, now we can go ahead and use the sum formula for the sine function. So that's r times, and here we have this sine of theta plus alpha will be replaced by sine of the first angle times cosine of the second angle, plus the cosine of the first angle times the sine of the second angle. Right? That's the sum formula for sine. Over here, this is the sum formula for cosine. But now if I distribute that r, that's going to give me r sine of theta cosine of alpha plus r cosine of theta sine of alpha. But now, just like before, you'll notice, hey look, r cosine of alpha, that's x prime. So here that's equal to x prime times that sine of theta. And over here we have plus that r sine of alpha, our sine of alpha, that's y prime, which gets multiplied by the cosine of theta. And there we go. So these are going to be our substitutions. In order to transform something from the xy plane into the x prime y prime plane, we simply need to substitute in x will be equal to x prime cosine theta minus y prime sine of theta, and y will substitute in x prime sine of theta plus y prime cosine of theta. Okay, but there's one thing missing though. What is the angle theta? Well, for that, we're going to refer back to our general form of a conic. Remember that every conic, whether it be a circle, an ellipse, a parabola, or a hyperbola, any non-degenerate conic, remember degenerate meaning the point or the line, has the form ax squared. And then when we last saw this, we skipped over a middle term here. We said ax squared plus cy squared plus dx plus ey plus f is equal to 0, where a, c, d, and e, and f are just regular real numbers. Well, now we're going to have one more term right here, and it's going to be b times xy. Without this term, rotations just don't happen. Anytime you have a term bxy, where whatever that b might happen to be, 2xy, 5xy, negative 1/6xy, whatever that might be, anytime you have a bxy term, that means that you have some conic that's been rotated. It will also help you determine how much rotation has occurred. Now, for the most part, I derive these results for you guys. I show you, okay, here is where this is going to come from. We build it from this. We have diagrams, or we have computations, or usually both, that show us where these results come from. This next result, I'm going to simply state the result of. Why? Is it too hard to derive? It's actually not hard at all. It's basic trigonometry. It's also a lot of trigonometry. Before I record any of these videos, I always go through and complete the proofs myself, just to make sure that they don't, they're accessible, make sure that I don't get to a point where I say, okay, now remembering your differential equations. Oh, wait a minute, you haven't taken differential equations yet, right? I always perform these proofs before the recording, just to make sure. This one, after about 45 minutes of proof of this one, I got to the end. And somehow I think there's a better use of our time than to have to see all of that. So it's not that this proof is inaccessible, it's just it is extremely tedious. There's a lot of very little steps, most of which are basic arithmetic: addition, subtraction, multiplication, division, factoring, and then simplifying. A lot of it. So in this case, we're going to skip to the result. So here, this is the general form of a, and I'm going to say non-degenerate. Remember, the degenerate conics are the point or the line. We don't worry about those. Of a non-degenerate conic. If you have this term, this is the one that tells you that there's some rotation. If this is not there, there's no rotation. It's a standard conic where one of your axes lines up either with the x-axis or the y-axis. When this one appears, that's the one that tells you rotation has occurred. If this is not 0, then rotation occurs. Okay? Not only does it tell you that rotation occurs, it tells you how much rotation. So here's that result that would take, it is doable, but it's also extremely long and tedious. The result, however, is fairly nice. The cotangent of double the angle that you're going to rotate by, remember that's what theta stands for, it's the angle that you're rotating by, the cotangent of 2 theta is equal to a minus c over b, where a is that lead coefficient, that number in front of your x squared. Here your c is the number in front of your y squared, and your b is this one here. Note that here, since we're assuming b is not 0, this will always be defined, which is nice. That means we'll always be able to get an answer. As long as this exists, we'll be able to find our angle. All right, so here, where Theta is the angle of rotation between axes. Rotation, let's say from the xy plane to the x prime y prime plane. So these are our two main results. This tells you how much rotation you have, and once you know how much rotation you have, this tells you how to apply that rotation. So let's take a look at an example. All right, we are going to, this is a multiple part problem here. We're first going to rewrite the equation that we're going to be given in a rotated x prime y prime plane system. Then, once we're finished doing that, we're going to write that new equation in standard form. The one in the x prime y prime system. Write that in, write the new equation in standard form. And then finally, we're going to graph. All right, so let's take a look. Our first problem will be x squared plus 4xy plus y squared minus 3 equals 0. All right, so here we go. The first thing we want to do is we want to figure out how much rotation needs to occur. 10 degrees, 20 degrees, 50 degrees. Or if we're doing it in radians, do we want to do pi over 6 radians, pi over 4, pi over 3? What are we doing? All right, so let's take a look. This is what will tell us how much rotation occurs. So first, let's find the angle theta. To do that, we can say the cosine, oh sorry, not the cosine, the cotangent of 2 theta is equal to, you're going to take the difference in your a and your c. Well, a is the number in front of your x squared, so that's 1, minus c is the number in front of your y squared, which is also 1, over b, which is the number in front of your xy term, your mixed term. Okay, so that's going to be 1 minus 1 is 0, over 4 is still 0. So we want the cotangent of 2 theta equals 0. Okay, well, the cotangent of 2 theta is equal to 0 at pi over 2. All right, so cotangent of 2 theta equals 0. That means your 2 theta is equal to pi over 2. All right, after all, if that 2 theta is equal to pi over 2, the cotangent of pi over 2 is 0. Oh, but now to find theta, all I have to do is divide both sides by 2. So I get theta is equal to pi over 4. For the most part, the numbers in our problems that are given in our assignments give us reasonably nice numbers. You're usually going to find things like pi over 4, pi over 3, pi over 2, pi over 6, things like that. In reality, if you're doing things, if you're doing this as an application for something, oftentimes your angle will be something like 17 pi over 38, or even worse, as a degree, it might be 17.94 degrees. All right. So note that most of the problems in this assignment, in this section, are going to give nice numbers, but also keep in mind that in application, you'll often find that's not so nice. All right, so first we find our angle theta, which we did. So now we're going to use that to find our substitutions. Next, find the appropriate substitutions. The appropriate substitutions are these. We know x is going to be x prime cosine of theta minus y sine of theta. So x is equal to x prime cosine of theta minus y prime sine of theta. Oh, but we know what theta is. It's pi over 4. So that's equal to x prime times the cosine of pi over 4 minus y prime times the sine of pi over 4. Oh, but we know what that is. The cosine of pi over 4 is root 2 over 2. And in fact, so is sine of pi over 4. So here that's going to give us x prime times root 2 over 2 minus y prime times root 2 over 2. This will be our substitution. Anywhere that we see an x in the original equation, we're going to plug in that thing. For y, we're going to do something similar. The substitution for y that we saw before, that we derived before, was y is equal to x prime sine of theta plus y prime cosine of theta. All right, so y is equal to x prime sine of theta plus y prime cosine of theta. But again, we know what theta is. It's pi over 4, so plug that in. So that's x prime sine of pi over 4 plus y prime of the cosine pi over 4. And again, we know what that is. Root 2 over 2 for both of those. So that's going to be x prime times root 2 over 2 plus y prime root 2 over 2. So first you find your angle theta using this right here. Cosine of 2 theta is equal to a minus c over b. And that'll help you find theta. Next, plug that theta into your substitutions to find what your substitutions are for this particular problem. And then third, take those and plug them in. Anywhere there's an x, you'll plug in this first one. Anywhere there's a y, you're going to plug in this second one. All right, so let's see what we get. Let's start with your equation x squared. Okay, so I'm going to leave a big blank there. There's my x squared plus 4 times x times y plus y squared minus 3 equals 0. All I've done is I've left blanks for all my x's and y's there. There is x squared plus 4xy plus y squared minus 3 equals 0. Well, now anywhere there's an x, so this first one and this second one, I'm going to plug in this stuff. Okay, so it'll be root 2 over 2x prime minus root 2 over 2y prime. And then same thing for this one. Root 2 over 2x prime minus root 2 over 2y prime. And then anywhere there's a y, I'm going to plug in this one. Okay, so in those two, I'm going to plug in root 2 over 2x prime plus root 2 over 2y prime. And same thing on this one. Root 2 over 2x prime plus root 2 over 2y prime. Right. So now, once we simplify, this will give us our equation. It'll mean the exact same thing, but it'll be in a new coordinate system that is pi over 4 radians, or 45 degrees if you prefer, 45 degrees offset from the original coordinate axis. All right, so let's go ahead and simplify now. We're going to take this and we're going to square it. Remember, whenever you have something like a minus b and you square it, that's a minus b times a minus b. You're going to distribute a squared minus ab minus another ab plus b squared. So your result is a squared minus 2ab plus b squared. If you, on the other hand, take something like a plus b and square it, that's a plus b times a plus b, which is a squared plus 2ab plus b squared. You're just distributing. All right, so we're going to do this one first. That's a minus b squared. Okay, so that means we're going to square this first one. Okay, well, if you square this one, you get rid of the square root of the numerator, and the 2 becomes a 4 in the denominator. So that's going to be 2 over 4 x prime squared minus double. You're going to multiply these two together. Okay, so root 2 times root 2, that's root 4, which is just the number 2, over 2 times 2 is 4 times x prime times y prime. Okay, so minus double that one times that one. And then plus, and then we're going to take the second one and square it, or b squared. So this, if you square this one, the square gets rid of the square root. Here, if you square the 2, that gives you a 4. And then y prime squared, like that. Okay. Plus 4 times, we're going to multiply these together. Okay, so now here we're going to have to distribute. There, 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 and there. Notice these are conjugates. That's the same as that one, and this one's the same as that one, but they have opposite signs. One's adding them and one's subtracting them. Remember that when you multiply together conjugates, a plus b times a minus b, that's a times a is a squared. That's going to be negative ab, but then that's going to be positive ab. And then negative b times b is negative b squared. But notice these two cancel out. ab minus ab, those give you 0. So when you multiply conjugates, you end up with a squared minus b squared. So right here, that's your a and that's your b, right? That's a minus b, and that's a plus b. Well, in the end, you're going to get the a squared minus the b squared. Okay, so let's square this first one. If you square the root 2 over 2, well, the square gets rid of the square root. And on the bottom, if you square the 2, you get a 4, x squared, minus, and now you're going to square the second part. If you square root 2 over 2, again, that's 2 over 4. And then you square the y prime, that's y prime squared. Okay. Plus, and I'm going to run out of room there, so I'm going to put it down here, plus. Now if I square this one, once again, that's this one here. So that's going to be almost exactly the same as this first one, except there's a plus here instead of a minus. So square the first one. That's 2 over 4 x prime squared, plus double the product of those two, root 2 times root 2, that's root 4, which is just the number 2, over 2 times 2 is 4, x prime times y prime, and then plus, and then you're going to square the last one. If you square this one, the square gets rid of the square root, and here if you square 2, you get 4, so 2 over 4, and if you square y prime, you get y prime squared. And then you have minus 3 equals to 0. All right. Some stuff simplifies now. In fact, a lot of stuff simplifies. Here, let me go ahead and simplify just numbers first. So 2/4, that's a half. So this would be 1/2 x prime squared minus, here 2/4 times 2. That's, oh, no, that's right. So that's going to be 2 times 2/4. That's 4/4. 4/4, that's just the number 1. So that's just 1 x prime y prime. And then here, 2/4, well, that's 1/2 y prime squared, plus. Here we can distribute the 4. So 2/4 is a half. So 4 times a half is 2 x prime squared. And then distribute the 4 there. That's going to give us minus 2 y prime squared. Again, we're just distributing the 4. That one there is the first one. And then here you got a minus, so that's going to be minus 2 y prime squared. Here, that one is, again, 1/2 y prime squared. Oh, sorry, that should be x prime squared, yeah. X prime squared. Here, 2 times 2/4, that's 4/4, which is just the number 1, x prime y prime. And here, 2/4 is the same as a half y prime squared. Minus 3 equals to 0. At this point, you may notice a few things combine or cancel. For example, here, x prime y prime minus x prime y prime, that's 0. and just goes away. On the other hand, you may notice that 1/2 x prime squared and another 1/2 x prime squared, that's 1/2 plus 1/2 is 1. 1x prime squared. Oh, but here I've got another 2x prime squared. So 1x prime squared plus 2x prime squared, that'll give me 3x prime squared. Like that. So 1 plus 2, that's 3 of the x primes being squared. And then right here, you may notice that we've got, that's 1/2 y prime squared plus another 1/2 y prime squared, that's 1 y prime squared. But then I'm subtracting 2 y prime squared. So 1 minus 2, that'll give us negative 1 y prime squared. Like that. And then the 3, well, that's just a 3. Like that. And now we have a conic in not x and y, like we started with. We started with this equation. But now we have it in x prime, y prime. Notice that after we've changed our coordinates, there's no more mixed term. Over here we started off with 4xy. Here we don't have anything like that. That's how we know we've successfully accounted for the rotation. Okay? All right, so this is the first part of the problem. We've rewritten the equation in a rotated x prime, y prime system. We learned that we rotated by pi over 4 radians, 45 degrees. And after we rotated by 45 degrees, we ended up with this equation. Without a mixed term, that means we've completed our rotation. The next part of our problem is we're now going to write that new equation in standard form. Okay, well notice that's a hyperbola. I have an x squared minus a y squared. Okay, x prime squared minus y prime squared. Either way, I have a difference of squares of x's and y's. That's what a hyperbola looks like. So let's go ahead and write this in the standard form of a hyperbola. So now let's write in the appropriate standard form, whichever is appropriate for that particular conic, which here we know it's a hyperbola. So 3x prime squared minus y prime squared minus 3 equals to 0. We can add the 3 over this way. That gives us 3x prime squared minus y prime squared equals to 3. And when you have a standard form for a hyperbola, it's supposed to be 1. So let's divide everything by 3. And now we have the standard form of x prime squared minus y prime squared over 3 equals 1. If you want to make that look a little more like what you're used to, you can write that x prime squared over 1, because usually you have x prime squared over a squared minus y prime squared over b squared. And here we can even take that one step further and write this as x prime squared over 1 squared minus y prime squared over the square root of 3 squared equals 1. And that way it really looks like, hey, x prime squared over a squared minus y prime squared over b squared equals 1. Either way, this would be an appropriate standard form, as would this. Either one would be fine. They mean the same thing. So finally, once you have that in the appropriate standard form, all that's left now is to graph. All right. So let's go and graph this. Let's begin with the standard XY coordinate axis. Okay. So if that's the standard coordinate axis, we know that we have an object that's been rotated pi over 4 radians or 45 degrees off of that axis. So along with our normal XY plane, which I'm going to write here as X and Y, I'm also going to graph another plane that's offset by this one by 45 degrees, pi over 4 radians. So here this angle is pi over 4. And so this is our x prime, y prime system. Okay, well now there we go. Everything's rotated now. So now we'll graph our equation in standard form, not on the original xy plane, but with reference to the x prime, y prime plane. All right, so let's do that. We're graphing a hyperbola. Okay, notice that nothing's being subtracted from x and y, so the center of this hyperbola is at the origin. The center is at 0, 0. We know that our value a, that's the denominator of the positive term, that's going to be 1. Right? And our b is going to be the thing that's being squared in the denominator of the negative term. So in this case, that's root 3. Okay? And for a hyperbola, to find our focus, or to find our foci, we're going to have 2 of them. We're going to have that, remember, c squared is equal to a squared plus b squared. For a hyperbola, it's a squared plus b squared. For an ellipse, it's a squared minus b squared. Here, when you plug those in, that's going to be what? 1 plus 3, that's going to be 4. So here c squared is equal to 1 plus 3 equals 4. Or in other words, c is equal to either positive or negative 2. So to find our foci, we're going to take 2 steps in either direction along the major axis. All right, so here we go. Along the transverse axis. All right, so here we go. We're graphing as if this were our axis. We're basically ignoring the original xy plane, and we're pretending this one in pencil is what we're graphing on. All right, so we're going to start from our center here. We're going to take 1 step along the x prime axis. Okay, so I should probably have some tick marks on here, shouldn't I? So I know how far to go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, and 5. Okay. Since x prime is the numerator of the positive term, that means that our transverse axis will be along the x prime coordinate axis. So here, our vertex will be 1 step in either direction, starting from the origin. So 1 here and 1 here. Okay? We will also have the square root of 3. We're going to take that many steps along the y prime axis. Now those will not be points on our hyperbola. Rather, they will be numbers that will help us determine how we can find our asymptotes. So here, the square root of 3, that's, 1 point something? Let's see, square root of 3 is about 1.7. So almost all the way to 2. And down this way, almost all the way negative 2. And now we have this box. If we connect the diagonals of our box, notice it passes through our center, and if we extend it on beyond the box, these will give us the asymptotes of our hyperbola. So that is the vertex of our hyperbola, as well as that one. So now we're going to have those follow along the asymptotes. So starting from here, up this way, and down this way. Likewise from here, going up, following along the asymptote this way, and down along the asymptote this way. Finally, we can find what our foci are, because we're going to travel along the transverse axis. Remember, the transverse axis is the axis that connects the 2 vertices. In this case, it's the x prime axis. And we're going to travel 2 units in either direction from the center. So our 2 foci would be 2 steps along this direction and 2 steps back along this direction. notice that this is a standard hyperbola in the x prime y prime plane. This is exactly what we would have seen in the first section when we first talk about hyperbolas. But now, note that if we rotate back and consider this with respect to our original xy plane, this is not at all a standard looking hyperbola. It is, well, it's tilted. Our transverse axis is not horizontal or vertical. And in fact, if we now erased all of this, if we erased the x prime, y prime axes, if we erased these lines that we got with respect to x prime and y prime, and we just left the hyperbolas, we would end up with something that is rotated. And our foci, likewise, would not be on the x-axis, and they would not line up parallel to the x-axis or the y-axis. So this is our final graph and our final result. We don't erase the x prime, y prime planes because it does help us see a little bit more clearly what we have done, how much we've rotated by. But if we did erase them, keep in mind that our x and y axes are the original ones. These are not actual axes in any system. They're just something that we use to help us figure out how this lines up. So that is our result. All right, so let's go ahead and have you try one. We're going to go ahead and do this one in stages. So go ahead and try the following. Consider the equation 11x squared plus 10 root 3 xy plus y squared minus 4 equals to 0. Eventually you're going to want the whole graph of this, but first what we're going to want is just the angle. So first, find the angle of rotation. Go ahead and do that in radians, because we'll generally do things in radians. All right? You're not looking for the full graph. You're not looking for all the transformations. Right now, you're just looking for theta. Go ahead and pause the video. Give yourself whatever time you need. And once you've found theta, go ahead and unpause, and we'll look at the next part of the problem. Okay, so we know that the cotangent of double the angle that we're looking for, the cotangent of 2 theta, is equal to a minus c over b, where a is the coefficient of the x squared term, minus c is the coefficient of the y squared term, and b is the coefficient of the mixed term, the xy term. Like this. So 11 minus 1 is 10 over 10 root 3. Since 10 over 10 reduces down to the number 1, really that's just 1 over root 3. So what that means is we're going to take the cotangent of some angle to give us 1 over root 3. That means that that angle must be, we can say degrees or radians, either 60 degrees or pi over 3 radians, but to keep it in line with the previous problem, I think I'll do this one in radians as well. So here that's going to be the cotangent of 2 theta is equal to 1 over root 3. That means that that angle 2 theta must equal to pi over 3. And so if I divide both sides by 2, that means the angle theta is equal to pi over 6. All right, so that's the first part. We found our angle theta. The next part is, let's go ahead and find our substitutions. That's going to be where we're going to find x is equal to something and y is equal to something. We're not going to plug it in yet. We're just looking for what is going to be plugged in. So next, find the substitutions. For x and y in terms of x prime and y prime. Okay. Go ahead and pause the video, give yourself the time that you need, and once you're done, go ahead and unpause and we'll go through that together. All right, so here we go. Our substitutions, x is equal to x prime cosine of theta minus y prime sine of theta. Well, we know what theta is. It's pi over 6. Okay, so then x is going to equal to x prime cosine of pi over 6 minus y prime times the sine of pi over 6. Okay. The cosine of pi over 6 is root 3 over 2. So that's root 3 over 2x prime minus the sine of pi over 6 is a half. So that's just a half of y prime. So there's our first substitution. X is equal to this. And then y is going to equal to x prime sine of theta plus y prime cosine of theta. Or in other words, x prime sine of pi over 6 plus y prime times the cosine of pi over 6. Which gives us that y is equal to the sine of pi over 6, again, is a half. So that's going to be 1/2 x prime plus the cosine of pi over 6, again, that's root 3 over 2 times y prime. And those are our substitutions. Now the third step is, in a way, the simplest because all you're doing is plugging in. But in a way, it's the most tedious because, well, then you have to simplify. So that's going to be your third step. The next part is substitute. And simplify. To get an equation in terms of x prime and y prime. Okay. So go ahead and pause the video. You're going to take these and just plug them in and then substitute and simplify. Right? Once you have the expression substituted and simplified, you've multiplied everything out, combined any like terms and so forth, then go ahead and unpause the video and we'll proceed to the next step. All right, so let's take a look. That's 11 times x squared plus 10 root 3 times x times y plus y squared minus 4 equals to 0. I've taken my original equation and left blanks for my x's and for my y's. So now let's plug in the appropriate expressions. Here for my x, here and here, I'm going to plug in root 3 over 2 times x prime, root 3 over 2x prime, minus 1/2 y prime, and same thing for this one. And then for my y's, here and here, I'm going to plug in this one right here. That's going to be 1/2 x prime plus root 3 over 2 y prime, and same thing for this one, 1/2 x prime plus root 3 over 2 y prime. And now we're going to simplify. Once again, remember that if you have a plus b squared, that's going to be a squared plus 2ab plus b squared. And if you have a minus b squared, that's going to be a squared minus 2ab plus b squared. So that's going to give us 11. Here that's a minus b squared. So we're going to start by taking the square of a, the square of this one. If you take the square of root 3 over 2, the square gets rid of the square root on top, gives you 3, over, if you square the bottom, that gives you 4. And if you square the x prime, you get x prime squared. Minus, double, you're going to multiply those two together. Root 3 times 1 is root 3, over 2 times 2 is 4, and then the x prime times the y prime is x prime y prime. And then plus, you're going to take the b and you're going to square it. You square the 1 gives you 1, square the 2 gives you 4, and then square the y prime gives you y prime squared. Plus, So that 11 applies to all of this stuff, plus 10 root 3 times. Okay, so now we're going to multiply this stuff. Here we're going to distribute. Right, we're going to have 1, 2, 3, and 4. All right, so let's see what we get there. When we multiply these first two, we're going to get root 3 over 4 times x prime squared. Root 3 over 4 times x prime squared. When we multiply the first one with the last one, we're going to get root 3 times root 3, that's root 9. That's just the number 3 over 4. So plus 3 over 4. And we're going to have x prime times y prime. Okay, so x prime, y prime. If we multiply these two, that's going to be 1/2 times negative 1/2. Okay, negative 1 times 1 is negative 1. Over 2 times 2 is 4. So negative 1 over 4. And that's also x prime, y prime. And finally, when we multiply the last ones, a positive times a negative is a negative. That'll be root 3 over 4. Root 3 over 4, y prime squared. Root 3 over 4, y prime squared. Plus, looking at this one now, that's a plus b squared. Okay, so you're going to take the a and you're going to square it. Okay. Squaring a half times a half, that's a fourth. And then you square the x prime, that's x prime squared. Plus double the a times the b. Okay, well 1/2 times root 3 over 2, that's root 3 over 4. And then the x prime times the y prime, that's x prime, y prime. So that's a squared plus 2 times a times b plus, now you're going to take your b, your last one, you're going to square that. If you square that numerator, that just gets rid of the square root, gives you just the 3. You square the 2, that gives you a 4. And if you square y prime, that's y prime squared. Like that. And then minus 4 is equal to 0. Okay. So we've gone ahead and multiplied out. We've squared and multiplied. Notice here we can distribute this 11 throughout here. We can distribute this 10 root 3 across here. All right, so let's see what happens when we do that. 11 times 3, that's 33 over 4 x prime squared. Minus 2 over 4, that's the same as 1 over 2. Okay, so here that's just root 3 over 2 times the 11. That's 11 root 3 over 2, x prime, y prime, plus 11 times a quarter is 11 quarters, y prime squared, plus, okay, let's see here. We're going to distribute the 10 root 3 throughout here. Okay, so 10 root 3 times root 3 over 4. Well, root 3 times root 3 is root 9, which is just the number 3. The number 3 times 10 is 30 over 4. And in fact, 30 over 4 can be reduced to 15 over 2. So 15 over 2x prime squared. Notice here these two are like terms. They combine. 3/4 of this minus 1/4 of this is 2/4. Or in other words, a half. So that's half x prime, y prime. And if I take a half of this, the 10 reduces to a 5. That's going to be 5 root 3 x prime, y prime. Here I combine those two and then multiply that result by 10 root 3. And finally I distribute here. So that's going to be minus, let's see here. That is, that should be a 4. I wrote that as a y. That's just sloppy handwriting. That should be a 4. So when we multiply, in fact, you'll notice it's the same number here, right? It's the same thing that happens over here. That's root 3 times root 3 is root 9. Root 9 is just the number 3. 3 times 10 is 30 over 4. And 30 over 4 can reduce to 15 over 2. So that's 15 over 2 y prime squared plus 1/4 x prime squared plus, here the 2 over 4 reduces to 1 over 2. So that's the root 3 over 2 x prime y prime plus 3/4 y prime squared minus 4 equals to 0. And finally, a bunch of things combine and simplify. First of all, notice that our mixed terms, there's 3 mixed terms, one there, and one right there. Here, these two have a common denominator. Let me write this one with a common denominator too. So instead of 5 root 3, I'm going to write it as 10 root 3 over 2. That'll make it a little easier to combine, right? If I have negative 11 root 3 over 2, and I add 10 root 3 over 2, that'll give me negative 1 root 3 over 2. And if I take negative 1 root 3 over 2 and add a positive root 3 over 2, well, that's all 0. So by combining these 3 terms, I just get 0, which is exactly what we want. When we rotate our axes, we're supposed to get rid of the mixed term. There are no more mixed terms left. So whatever's left will now be rotated enough to be in the new x prime, y prime system. So let's go ahead and combine whatever's left. Here I have an x prime squared, and here's another x prime squared, and here's another x prime squared. And if I combine all of those, well, let's see, 33 over 4 plus 1 over 4, that's 34 over 4. Let's write that right here, 34 over 4, plus 15 over 2. Notice those reduced right here, 34 over 4, that's 17 over 2, plus 15 over 2, and that's what, 32 over 2, which is just 16. So all of these canceled out. These 3 combine to give me just the number 16, x prime squared. And then these combine over here, that one, and that one. Oh, let's see here. I have 11 fourths plus 3 fourths. Okay, so 11 plus 3, that's going to be 14 fourths. 14 fourths. Now I'm subtracting 15 halves. Now 14 fourths, that's the same as 7 over 2 minus 15 over 2. That'll give us a negative 8 over 2, which is really just negative 4. So that's negative 4 y prime squared. And then that constant, it doesn't combine with anything else. Everything else is already combined, so that negative 4 will just stay negative 4 equals to 0. And there we go. We've substituted and simplified. So now our original equation, this 11x squared plus 10 root 3xy plus y squared minus 4 equals to 0, after a rotation of pi over 6 radians, a rotation of what, 30 degrees, we end up with, in this new coordinate system, 16x prime squared minus 4y prime squared minus 4 equals 0. Notice what kind of conic that is. We can now put this in standard form in the x prime y prime system. So that's our next step. This is a very short one. Write in standard form in terms of x prime and y prime. So take this and write it in the standard form. Make note of what kind of conic it is. That should be a fairly short one. Go ahead and pause the video, and once you have this written in the standard form, go ahead and unpause and we'll go through that together. All right, notice that you have the difference of squares here. That's going to be a hyperbola. All right, so that's going to give us, we want the constant over on the other side. So that'll be 16x prime squared minus 4y prime squared equals to 4. And then in the standard form of a hyperbola, we want the constant to be 1. So we're going to divide everything by 4, and this will give us 4x prime squared minus y prime squared equals 1. And there we go. That's the standard form. Now, this might look a little off because usually you're going to say, well, isn't that supposed to be a fraction? Aren't I supposed to have x prime squared over something? Why is that times something? Oh, well, we can rewrite this as x prime squared over 1/4 minus y prime squared over 1 equals to 1. After all, dividing by a fraction is the same as multiplying by a reciprocal. Dividing by a quarter is the same as multiplying by 4. So here these mean the same thing, but now that looks a little more like what we're used to. X prime squared over a squared minus y prime squared over b squared. So here this is fine. This is correct. This is in the standard form. However, you may not recognize that as being the standard form, so if you prefer, you can also write that this way. Either one is acceptable. So the last step of the problem is go ahead and graph. You now know what this looks like in the x prime y prime coordinate system, and you know that the x prime y prime coordinate system is offset from the traditional coordinate system by pi over 6 radians, which of course is the same as 30 degrees. Right? We're doing everything in radians, but it's the same as 30 degrees. So go ahead and, that is the last part of the problem. Go ahead and graph. Take this result, 4x prime squared minus y prime squared equals 1, and go ahead and graph that on the x prime y prime plane, which of course is offset from the traditional plane by 30 degrees. Go ahead and draw the traditional plane as well. So for your last problem, graph the conic and here, let me go ahead and write down what that is. You're going to graph the conic, which was 4x prime squared minus y prime squared equals 1, which was the same as saying x prime squared over a quarter minus y prime squared over 1 equals 1. Go ahead and graph that on the x prime y prime plane, which of course is offset from the original plane by 30 degrees, by pi over 6 radians. Go ahead and pause the video now, and once you are done, go ahead and unpause and we'll finish the problem together. All right, so let's go ahead and take a look. So here we have our coordinate axes. Notice I've drawn the traditional xy coordinate axis, the x being horizontal, the y being vertical, but I've also drawn the x prime and y prime coordinate axes, which here are 30 degrees, or pi over 6 radians rotated. All right? Here I didn't take the time to grab a protractor or anything. I simply drew them approximately, right? That is sufficient for this. All right. So now, for the time being, we're going to ignore the xy coordinate axes. They're still there, but we're going to graph everything with respect to the x prime, y prime axes. All right, so here we go. Here, this can be written as x prime squared over 1/2 squared. After all, 1/2 times 1/2 is a quarter. Minus y prime squared over 1 squared equals to 1. So here our our transverse axis will be along the x prime axis. Okay? And in fact, it will be 1/2 of a unit out in that direction. So I guess I like being consistent, and I will. I once again forgot to make my tick marks, so let's go and do that. So let's see. That's well, these aren't going to be very big, are they? So let's keep them a little bit further apart. That's 1 and 2, and that's 1 and 2. I like to be consistent with the things that I forget and make mistakes on. You know, it makes everything easier. There we go. Okay, so our transverse axis is along the x prime axis. So from the center, which you notice is 0, 0 in this case, we're going to travel 1/2 of a unit along the x prime axis to find our vertices. So that's 1, so we want to go about halfway out. And same thing over here, that's -1, so we want to go halfway out. Here we want to then take one step along the y prime axis, and even though these points will not be part of our graph, they are going to help us find the asymptotes to shape our graph. So now we're going to go ahead and draw our box. That is here from the center, up by B, down by B, right by A, left by A. And now if you connect the opposite corners of this box, you end up with your asymptotes. Here it looks like the asymptote is the y-axis. Now here I didn't take the time to be precise enough. Here you'll notice that these angles aren't maybe not exactly 90 degrees. This is not a super precise graph. It's good enough for what we're doing right now. So right here it does look like our other axis is the y-axis. Sorry, it looks like our asymptotes are given by the y-axis, but I can't be 100% certain on that. However, it does look to be about right. All right, so now we know that here are our vertices along our transverse axis, because since that is the variable in the numerator of our positive term, that means that our vertices are found along that axis. And if those are our vertices, we then have a hyperbola that goes from that vertex out along the asymptotes, and likewise over here from this vertex up and down and out along the asymptotes. Something like this. And finally, we can find our foci, because after all, c squared is equal to a squared plus b squared for a hyperbola minus for an ellipse. And so here that means that c squared is equal to, well, our a squared was a quarter, and our b squared was 1. So that's going to be 1 plus a quarter, that's 5 quarters. And if I take the square root of both sides, that gives me c is equal to root 5 over 2. Root 5 is about 2.2. So if I cut that in half, that's about 1.1. So our foci will be found along our transverse axis, which is the x prime axis. And we're going to go forward 1 and a little tiny bit past that, about 1.1 in either direction. 1.1, give or take. So those will be our two foci, our asymptotes, and our graph. So here you note that you have a fairly standard looking hyperbola on the x prime y prime coordinate axis, but now if you take a step back and consider that on the traditional xy axis, you'll notice a not so standard hyperbola, rather one that's been rotated by pi over 6 radians, by 30 degrees, so that our asymptotes are now here, so that our transverse axis and our foci no longer line up along with the x or the y axis, but rather are rotated off by 30 degrees, by pi over 6 radians. And this is our final result. This is our graph. All right. Lastly, it is often going to be useful to know what your answer is going to look like before you even start. Here, I've gone through and I never quite knew what I was going to get until I actually got it. I never actually knew what was going to happen until I found the angle of rotation, found my substitutions, substituted, simplified, and ended up with a general form conic. At this point, I knew what was going to happen. Then I was able to put it in standard form and graph. But notice that for most of the problem, I don't know what kind of conic I have. Note also that if you look at the original problem, this doesn't match up with what we're used to. Normally, if you have x squared plus y squared, that's a circle, or if you have different numbers here, that would be an ellipse. That didn't happen here. Our original problem was x squared plus y squared, and yet we ended up with not an ellipse, but a hyperbola after we accounted for our rotation. That's because this mixed term throws off what we're used to when we don't have a mixed term. When we're missing an xy term, then, okay, sum of squares, that's a ellipse, a difference of squares, that's a hyperbola, and if only one of them is a square, that's a parabola. But apparently with a mixed term, that no longer applies. Okay, so if there is a mixed term, is there any way to tell what kind of conic I have? Yes, and in fact, it is a very familiar looking expression. It turns out that if you have a conic in the general form, ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. If you have a non-degenerate conic in this form, then the determinant is the same determinant that you're used to when you deal with the quadratic formula. If you take b squared minus 4ac, the value of this will tell you what kind of conic you're dealing with. Note that that's not at all necessary when you don't have that bx squared, that bxy term, because if you don't have that, then you're left with just negative 4ac, or in other words, you're left with what we had in previous sections, where, oh, if those are added, that's an ellipse. If they're subtracted, that's a hyperbola. Or if one of them's missing, either that one or that one, then you have a parabola. But if you do have a bxy term, then the result, b squared minus 4ac, if that is equal to 0, then you have a parabola. If you have b squared minus 4ac is greater than 0, you have a hyperbola. And if you have b squared minus 4ac is less than 0, then you have an ellipse. So if you go back to our previous question, before we did any of our computations, just at the very beginning, we had 11x squared plus 10 root 3xy plus y squared minus 4 equals to 0. If we find b squared minus 4ac, here note, b squared minus 4ac is equal to, well, that's your b, so let's square it. 10 root 3 squared minus 4 times our a is 11 times c is 1. If you square 10, that's 100. If you square root 3, that's just 3. So 3 times 100 is 300. Minus 4 times 11 is 44. Times 1 is still 44. If you take 300 minus 44, you end up with, what, 256? Which is definitely greater than 0. So that means that b squared minus 4ac, your determinant, gave you a positive number. So that means that in the end, your conic, well, it is rotated and it's a hyperbola. So the graph will be a rotated hyperbola. It's often useful to know how to do this at the beginning of a problem, because if you make a mistake, it's kind of hard to know that you've made a mistake. If you perform the initial computation wrong, you'll have the wrong angle. If you perform the initial substitution wrong, you'll have the wrong conversion factors. And if you perform this substitution incorrectly or simplify incorrectly, you'll end up with something that is maybe the wrong conic. Maybe you'll have a plus instead of a minus here. Or maybe you'll accidentally cancel out a term when it shouldn't have been canceled. So it's a long enough problem that mistakes can happen. Knowing ahead of time what your conic is supposed to be will often help you determine if a mistake has happened. At the very beginning, you know this is a rotated hyperbola. Hey, look, at the very end, I got a rotated hyperbola. That gives me a good amount of confidence that I did this correctly. However, if in the end I had gotten a rotated ellipse, or a rotated line, or a rotated anything else, or if I had gotten a hyperbola that wasn't rotated, well then, certainly that must be wrong. So it is often useful to be able to perform this quick computation at the very beginning. It doesn't actually give you anything that you don't already have. At the end, you got that answer. It's a rotated hyperbola. However, this does help give you a bit more confidence that everything works out correctly because you know ahead of time what your answer is. Not only that, but if you know ahead of time what your answer is, you'll know what you're aiming for so that sometimes your computations are just a little bit simpler if you know what's supposed to happen at the end. Right? So that is it. keep in mind that this works for any, this is for any non-degenerate, the general form of a non-degenerate conic. Non-degenerate meaning not a point or a line, either a parabola, an ellipse, or a hyperbola. Note that in ellipse, it will also include a circle. So in the end, if you have b squared minus 4ac is less than 0, you might get that you have an ellipse. And in the end, when you graph it, it turns out to be a circle. A circle is just a special form of an ellipse. So here, let's make a note of that. Ellipse also includes the circle. That. There is, however, the three main conics, parabola, hyperbola, and ellipse that we were concerned ourselves with. So that's it. That brings us to the end of our section, and that brings us to the end of our topic. If anybody has any questions, comments, or problems, please let me know, and I hope everyone has a nice day.